I posted the key. Do review the key, review your answers, review my added points. If you feel that you have any other questions, come to me directly or email me and I will look at things with you. Okay, but you guys did really well, so that's good. And if you didn't do as well as you wanted, that's okay. There's still the final and one more quiz. And of course, all of your lab reports. I will be having review session on, was it December 14, the Wednesday, last day of class during lab. So that week you won't have lab and I'm not gonna do a review session on Monday and Wednesday. So please, all of you come on the Wednesday. If you can't, for any reason, let me know, but you probably wanna be there because I go over a lot of questions that will turn up in the final. So it's important to come to that review session. So keep that in mind. The last week of classes, you don't have lab, but you have a review session on Wednesday. So the final will be similar to the midterm in terms of how the questions are framed. It will be just longer. Yeah, you're going to be writing a little more, but it would be very similar to the scenarios that you see in the midterm. Okay, so why is this in the middle? Go away. Thank you. All right. Let's recap. What is the basis of carbohydrate analysis using enzymes? So what do I mean by this question? I'm trying to think what I meant by that question. So basically, let me try to explain what I mean. Is that when you use enzyme for starch, what are you trying to do? You break up all of the units, all of the starch polymers into monomers. And then we use enzymes that will give you a chromophore that will absorb light so that you can measure absorption, either of the reactants or the products. And usually, oftentimes it is two-step reactions or dual enzyme reactions where you have the first equation, which is the measuring reaction or auxiliary reaction, and then the next reaction with the second enzyme, we call it the detecting reaction, where we get the chromophore to measure absorption. So what I mean by basis is that at the end, you have a chromophore to measure the absorption and relate to the constituents using standard curves. Okay, so I asked the question, I answered it myself.
In every enzyme analysis, do you always go to glucose?
Not necessarily,
Okay.
because in starch you go to glucose because the glucose is the makeup, the monomer. But sometimes enzymatic reactions are to determine sucrose, for example. So there is a specific kit for sucrose detection, and it doesn't have to be down to glucose. So what are the enzymes involved in starch analysis? So first, we need an endoenzyme. Do you remember what it is? It's a very common one, Taylor. Alpha amylase. So the alpha amylase is going to chop down your amylose and amylopectins into small, short-term maltodextrins. And then what happens after that? To get the glucose, you can read from your notes. What do you use? Glucoamylase. Oh, it's faster. Okay, so we get glucoamylase to break down those small maltodextrins into, do I get +2? To get to that monomer unit, which is glucose. It's too low, this thing. Okay. Oh, why am I in the field? Let me change my background to show them. change the background. How do I change the background while I'm here? Okay. I was in the field. Now I'm in the class. All right. So we stopped at dietary fiber. We talked about the different components of dietary fiber. We talked about soluble and insoluble dietary fiber. This crude dietary fiber determination used to be common a few years ago to determine total fiber in food, but then it's no longer used for food and labeling because it doesn't give you all of the dietary fiber components. So it's now used only for animal feed. If you don't find it in your textbook, but I'd like to keep mentioning it because we need to know when somebody comes and say, can you do crude fiber determination for us on this? I have to tell them this is not the method to do it in food. It's now the method to do it for only animal feed. So why? Because both methods, acid and alkaline extraction, you will lose pectins, you will lose soluble dietary fiber, because here the acid and alkaline basically hydrolyze everything, and the insoluble fibers will precipitate, mostly cellulose and lignin. So, and same with detergent extraction. Also, you lose mostly the soluble dietary fiber. So it's not sufficient for determining total dietary fiber for humans. So we do a more complex kind of analyses to determine the fiber. We don't have a lab on this because I wished we had a lab, but it's very, very long process. It takes a really long time to get it done over a few days, kind of. So why is it over a few days? I'll tell you later. But when you start with a food product, you want to remove the moisture. So you would dry it, you would defat it, and then you have mostly your protein, starch, and dietary fiber in there. You want to get rid of the proteins and starch. You want to solubilize them out and just keep the dietary fiber. So the way you do that, you do digestion with enzymes. So you start with alpha amylase, you heat the sample so that the starch is gelatinized, so it will be more effective hydrolysis of the starch. And then you would also add glucoamylase because you want to solubilize all of the maltodextrin so that you have glucose that will be in the aqueous portion of your acid. And then you want to break down the proteins onto amino acids. So you want to solubilize the proteins as well. So you use a protease in this reaction. So you heat, gelatinize the starch during heating, break down the starch by alpha amylase, break it even more by glucoamylases, and then digest with the protease. So what you end up having, you adjust the pH and temperature for optimal enzyme conditions, and then what you end up having is your dietary fiber, the soluble will be with the solubles, and then you have the insolubles that would precipitate. But you don't want to lose the solubles, so you would precipitate all fibers, soluble especially, with ethanol. So if you add ethanol, your soluble fiber will precipitate. Then you can separate, filter out the solubles that would have glucose and amino acids and some minerals. And then what you end up with is your dietary fiber, total dietary fiber. So you wash it several times with alcohol, you dry, and then you have the dry matter, but there might be residual protein or amino acids or residual nitrogen, basically, and you might have residual ash. So what you do is you measure protein and ash in that dry powder and you subtract it from the weight. Then you get the total dietary fiber weight. So it has to be corrected. And that's why I say it takes multiple days to do, because you can do this in one day, but then you have to dry, and then you have to do Kelda, not Nico. It doesn't work with Nico because you have a lot of components that would plug the crucibles in the Nico. So we don't do that. We don't do nitrogen analyzer. We use Kelda, so it takes more time, and we do dry ash. So that's why it's an extensive method to be able to actually do it in the lab, or even have you do parts of it in the lab. Now I get total dietary fiber this way, but if I want to get soluble and insoluble dietary fiber separate, so I don't wash here with ethanol. So what I do is I have the soluble and I have the dietary fiber that is insoluble. I filter and wash, and I get two components. I have the aqueous that have my soluble fiber, and I have the non-soluble fiber. So I separate those. So the one that is the residue on the filter, that would be your insoluble fiber. You wash with water, ethanol, other alcohol, dry, you weigh, you correct for protein and ash. You get the insoluble fiber. Now, the filtrate, after filtering, the filtrate that goes through have your sugars, amino acids, soluble fiber in it. You want to get that soluble fiber, then you precipitate with ethanol. Then you get the precipitate, which is now your soluble fiber, and your other solubles. So then you filter, the precipitated soluble fiber stays on the filter, you wash with alcohol, you dry, you weigh, and then you get you do the protein and the ash, subtract the weight of the protein and the ash, and then you get the weight of your soluble. If you follow that route, you get soluble and insoluble, you can add them, and then you get total dietary fiber. But sometimes it's really important to know how much soluble dietary fiber you have versus insoluble due to the physiological differences between soluble fiber and insoluble. So it's important to report both figures. Okay. Now, if you want to identify what type of dietary fibers you have, do you have pectins, hemicelluloses, celluloses, lignins? So in order to identify, you get your insoluble and soluble, and then you break down glycosidic bonds. So you break down glycosidic bonds to basically get neutral sugars and then uronic acid from pectin. Pectin is the subunits of pectin. Pectin is galactouronic acids. So you cannot determine that by GP, we do calorimetric detection. But the neutral sugars that come out of our different dietary fibers, we can measure or determine the composition using GCFIP. So basically here the same thing, you get rid of the starch, you get rid of the protein, and then you hydrolyze by acid to free monosaccharides, the units of your dietary fiber. Then you can measure those by GC and then colorimetric method, specifically for uronic acid that come from pectin. Speaking of pectin, there are some food products that have pectin as the sole dietary fiber in them. Nothing else, because it's used to form the gel matrix. So, for example, in jams and jellies, in order to determine the amount of pectin, so you would want to saponify, because the glycosidic linkages is very hard to hydrolyze by an acid. So what you would do, you do saponification. So these are the units. So you have galactouronic acid that are methylated. So you have a methyl group here sometimes, not in all units. then what you do with subamplification, you de-acidify. So you remove that methyl unit. So you have all of them as carboxyl groups ionized with a net negative charge. So there are all net negative charge. What you can do, you add calcium. So the calcium will react with your net negative charge and kind of precipitate your pectin. So that's why it's important to subamplify to break up the methyl groups and give you all ionized group that would form complexes with the calcium and form calcium pectate, actually precipitate, and then you can measure gravimetrically. So this is an exercise that I want you to do, I think for +5, I believe this exercise, not now. So you can do that as extra credit homework if you're interested in getting 5 points. So this is the data that we usually get when we run dietary fiber. Since we will not run dietary fiber in lab, I want you to be able to kind of visualize what happens by dealing with data. So what we do usually, we use crucibles that we use for filtering, okay? So we take the weight of the crucibles because that's where your fiber, residual fiber will be in. So we take the weight of crucible where we got our insoluble fiber, the first step after solubilizing starch and protein, breaking them down. If we filter, we get the insoluble fiber. And then later on, we take the solubles and we add ethanol to precipitate the soluble. So the first step is getting the insoluble. So we take the weight of the crucible that we use and for the insoluble fiber, and there's another crucible we use to filter out the soluble fiber after we precipitate. So we do that in duplicate. So we take the first crucible and the second crucible for insoluble, and we take the weight. So these are weights in grams. And then we take the weight of the crucible plus the residue, either insoluble fiber or soluble fiber. So you would have the weight with the residue. So if you subtract the crucible from the crucible plus residue, you get the weight of the insoluble fiber and the soluble fiber. However, we need to do protein to determine, to remove the residual weight that is due to protein. So we do Kelvin and we get how much grams of protein we have. You notice that we use 1 rep to get the protein and another rep to get the ash, because we won't be able to do protein and ash on one sample because they destruct the sample. So because you won't be able to retrieve it. So you take 1 rep, you put it through CalDot, you get the protein content. You take the other rep, you put it through dry ashing, and then you get the ash content. So this is, you have to subtract the crucible to get the weight of the ash. So you have that for insoluble and you have that for soluble. And you run a blend, you always run a blend for any contamination due to reagents. So your blend, you treat them the same way, and you get values of protein in blank and also of ash in blank after you subtract the crucible. So what you need to do now then is after you get the protein and the ash content, you subtract them from the weight of the insoluble fiber and you do the same for soluble, then you can get the actual insoluble fiber, actual soluble fiber, you add them, you get total active fiber. So do this exercise and this is kind of guiding you through how to do it. So do that, and let's see, today is Friday. When would be a good time to return it? You don't have any lab reports due next week, right? Do you want to do that before you go on holiday by Wednesday, or do you want, yeah, it's because you know you have lab report due on Sunday evening, right? Monday evening? When do they have a lab report due? What was it for, the full lab report?
Yeah.
After,
Yeah, is that due on Monday next?
Yeah.
after.
Okay, so let's get you guys giving me this on Wednesday for extra credit, so that you don't have to worry about it. Okay, only if you want to, +5. All right, so this is that. I have enough time to at least talk you through fat characterization, which would be the lab after you come back from Thanksgiving. So next week, Monday and Wednesday, I won't be here. You'll get a lecture from my postdoc on protein characterization, one of my favorite lectures, but I'm missing it. Anyway, my postdoc is good. She will do a good job going over that. So I wanted to start the fat characterization, which would be the subject of your lab when you come back from Thanksgiving.
Professor,
Yeah.
we do have lab next week, though, right?
Yes, you have lab on Monday and Wednesday to do total carbohydrate.
Oh, I see.
Yeah, so you have lab next week. But Monday and Wednesday, I won't be here to lecture. That's why it's gonna be covered by a postdoc that would be more comfortable. She's more comfortable covering protein characterization. So therefore, I'm starting fat. So you have some idea for the next lab, which is after you come back. Okay, I don't want to confuse you. Next week is total carbohydrate lab. Yeah. All right. Let's see what you guys know. And again, you're here to learn, no judgment, but let's see. Peroxide value is a measure used to detect advanced stages of lipid oxidation. So here you're going to try to remember lipids in this lecture. Lipid oxidation, and what are the metabolites of lipid oxidation? Measuring of hexanal gives an indication of advanced stage of oxidation. Iodine value can be used to detect oxidation. I don't think you're gonna know this, but let's see if you can tell me if A is true or false. Lipid oxidation, try to remember what you learned about lipid oxidation. What's the first metabolite of lipid oxidation? First class of metabolites. Peroxides. So they are first metabolites. They are not detect advanced stages of oxidation. It's peroxides are the first metabolite that would come out of lipid oxidation. Hexanal is secondary metabolite. So presence of hexanal is an indication of advanced stages of lipid oxidation. So no, yes, and for this, put yes next to it. And I will talk about iodine value. Probably I won't get to it today, but iodine value is basically a measure of unsaturation. So it's a reaction where you have double bonds in your unsaturated fat, and then iodine is going to react, and you will break the double bonds, and then you will replace with iodine. So the more double bonds you have, the higher iodine value you get. So remember that will be important for your lab. So iodine value is a measure of degree of unsaturation. Now, can it be used to detect oxidation? Well, it's not a direct method, but if you know the initial iodine value of your fat, oxidation is going to attack double bonds. So an oxidized oil or fat will have lower iodine than a non-oxidized oil or fat. Because iodine is going to attack the double bonds, and if the double bonds already broken due to oxidation, you will have a lower iodine value. So keep that in mind as we go through the lecture, and that will help you again with the lab as well. Now, you're going to do saponification value in lab as well. And the saponification value, so this is false for you guys. This is kind of studying, and later on you'll know that this is false when we cover that. So it has nothing to do with fatty acid saturation. That is iodine value. It has to do with the length of the fatty acid. So the average molecular weight of the fatty acid. So having saponification value, you can actually calculate the average molecular weight of fatty acids, which is an identification tool. It's very unique to different oils and fats. So it's a unique property. And then with saponification value, you can detect adulteration. So it is an identity that is unique for different fats and oils. So when you come back from Thanksgiving break, you will have a lab on fat characterization. You're going to go back to the formulation of working with your group, your original rotation groups. And you are going to do, each group will get assigned a specific oil. And you're going to share data, and you're going to look how different oils have different saponification value. So the saponification value has an inverse relationship with the average molecular weight of your fatty acid. You have to remember that, inverse relationship. You're going to see it when we calculate. But I want you to remember, the higher the saponification value, the lower is the average of your fatty acid in that oil, or the average molecular weight of fatty acids in the oil. So inverse relationship. So I want you to remember that for now. Okay. Why is it important, or what's the importance of fat characterization? Stella.
For standards of identity.
Standard, I won't call it for oil standard of identity, but it is, you want to identify the authenticate the identity of the oil. So one thing is authenticating the identity of the oil. What else? Health concerns. Huh? Health concerns. Health concerns. If you have oxidation products, such as cholesterol oxide or malonyl aldehydes, these are secondary oxidation products that are cancers. So definitely we want to do that for safety and health reasons. What else? Kevin?
Pointing crystalline structures for like functionality of food.
Yes, so there is like solid fat index or the melting point and spreadability. So these are all important for functional and texture of the different fats, like in margarine, for example, how well it can spread compared to butter. So that have different solid fat index. Okay, what else? There's important thing, Taylor. Quality. So basically, I would say shelf life, stability over time. How would the oil, would it oxidize too fast? Would it be stable over the shelf for a certain period of time? Sometimes we add antioxidants. So we look at the stability of the oil with and without antioxidant and determine if natural antioxidant would be good versus synthetic antioxidant. So stability. There is important. Do we care about fat characterization for nutrition label? What's on the nutrition label? Saturated. And what else? Trans fat. Yes. So you guys are really good. So here we are. So nutrition labeling here. part of fat characterization is not only like here, we're not going to only care about total fat content, we care about the composition. So we have total, but we also look for saturated fat and trans fat. So for the method that you learned in the lab for fatty acid composition, this is the method that we use, but we do use quantitative, not semi-quantitative like we did. So we would run standards and run calibration curves so we can get fatty acid composition. And with the fatty acid composition, we can back calculate how much total fat we have. That's the official method of getting total fat by doing the fatty acid composition. You don't do Mojo, you don't do Soxlet, you do composition by fatty acid composition to get total fat, to get saturated fat, to get fat. Okay. Shelf life stability, you talked about that. Processing effects. I want to introduce some processing effects. Can you give me an example of processing that involves oil? What is very common? What does McDonald's sell? Right. So deep frying. What happens to the oil when you deep fry? You put your wet potatoes, high moisture content, you put it in the deep fryer. What happens? The moisture evaporates. Well, moisture evaporates, but before it evaporates, it does something to your fat with the heat. High moisture, high heat. What happens to the triglycerides? Yeah, hydrolytic rancidity. Not with enzymes in this case, with high temperature and moisture. It will drive the reaction towards breaking down the triglycerides to free fatty acids. Then when you have high free fatty acids, what happens to the oxidation? Increases, increases. So high amount of free fatty acid has higher rate of oxidation than when they are esterified to the glycerol. So triglycerides have lower rate of oxidation. So have you heard of oil refining? What does this step do to the crude oil? What do you know what refining does? Do you cover this refining in any of your classes? You talk about refining?
Yeah, there's one specific about brine and then one specific about oils.
Yes, so great. So what do you remember about the refining process? What does it do? It's okay. If you haven't covered it in detail in other classes, you wouldn't know. So the crude oil has a high percentage of free fatty acids. So when you crush your olives, for example, or crush your soy or whatever, you're going to get a crude oil that has free fatty acid in it. If you don't do refining, shelf life will be short. Because the fatty acid not only is going to give you like this unique flavor, but also through oxidation, but also it's more prone to oxidation than triglycerides. So the refining process, what they do is they actually add an alkaline solution. They add NaOH. So fatty acids are acids, right? So the NaOH is going to react with the acid, going to give you soap and water. Yeah. So then they do centrifugation, they get rid of that soap, and then you have a refined oil. So of course, it's going to go through deodorizing and a lot of winterizing and a lot of different processes. But the first process is to get rid of fatty acids, free fatty acids. So in the lab, one group is going to get virgin olive oil, another group is going to get refined olive oil. And you're going to see a difference in the fatty acid content. And you're hopefully, if the experiment works every year, we kind of like either hit or miss. Hopefully you'll see higher peroxide value over storage than refined. Palatability and sensory effect, when we do spreadability, when we do solid fat index, we're really looking at that sensorial texture feeling, and then safety, obviously. Okay, so Like I said, we care about, oh, cholesterol is also another one on the nutrition label. So saturated, unsaturated, trans fat, cholesterol, we need to know all of this for the nutrition label. Talked about shelf life. We have oxidative rancidity. We talked about that. Hydrolytic rancidity can happen over storage. So during frying, you have hydrolytic rancidity breaking down with the presence of water and heat. But what else can cause hydrolytic rancidity, let's say, in oats? Huh? Lipase. So you have endogenous lipases in oats, in wheat, in whatever you have. Sometimes you have endogenous enzymes that would potentially cause breakdown of your triglycerides over time. And then sometimes also you have endogenous lipoxygenases. These are enzymes that cause oxidative rancidity. So oftentimes processing tries to inactivate those enzymes, lipoxygenases, lipases, trying to get rid of them to prevent hydrolytic rancidity over time. Because if this happens, this is going to be speeded up. If hydrolytic rancidity occurs, oxidative rancidity rate will increase. So if you have lipase, lipoxygenase in your system, good luck, you have rancid oil, rancid product. So oftentimes, I give you an example about why is this problem. In protein ingredients, so let's say pea, you think it doesn't have a lot of fat, but even if you have 1% or 2% fat in your protein ingredient over storage, the endogenous enzymes is going to cause hydrolytic rancidity, oxidative rancidity, and then you get this off flavor, and they blame the protein. It's not the protein fault. It's what comes with that crop. So basically, this is important. These shelf life stability is important, even in products that have very low fat content, because the products of oxidation, you have very low threshold. So you can, perceive them, because they're mostly odor. But when you eat, you have the flavor comes into place, the taste and the odor, and you have that off flavor. There are ingredients that are developed to mimic lipid and doesn't have caloric value. So olestra is one where it's really a sucrose with fatty acids, 6 to 8 fatty acids. It does not contribute to 9 calories per gram. Basically they use short chain, medium chain fatty acid. So it gives you the same mouthfeel potential, similar, but you're not getting the caloric intake. So we need to also understand the use of different types of ingredients that mimic lipid or have functionality similar to lipids. Okay, so processing effects. So we talked about deep frying. We didn't talk about hydrogenation. So margarine is what? A hydrogenated vegetable oil, right? So you get the vegetable oil, and how do you make it solid at room temperature? The hydrogenation. So basically hydrogenation attacks double bond and break the double bond, and then you will have saturation with hydrogen. So the more saturated the fat or oil is, the more it's going to be solid at room temperature. So hydrogenation causes changes in the saturation. And if you have incomplete hydrogenation, sometimes it causes the production of trans fat. So incomplete hydrogenation, you might have, so you have, in nature, you have cis fat. When you hydrogenate, and if it's incomplete hydrogenation process or something faulty about your hydrogenation process, you can get a difference in, you can still have double bonds, but instead of being cis, they become trans. So trans fats are a no-no. You want a zero trans fat on your label just because trans fat is associated with cardiovascular diseases. So that's why it's very important when we have your name, we test the production of trans fat. Okay, we talked about refining. We have to get rid of the fatty acids. Do we know what winterizing is? It's another process. In oil, you have waxes sometimes. So they are the crystalline fats that crystallizes. So if you reduce during processing after refining, deodorizing, then you winterize, that means you bring down the temperature of the oil to cold temperature, then your waxes will precipitate, then you clarify the oil. Why? Because sometimes you have salad dressing with high amount of oil. You don't want it to look cloudy over storage in the fridge. So you want to get rid of that crystalline fat, the waxes, through winterizing. We talked about palatability, we talked about oxidation products for safety. Okay, good. So the methods that we will be covering in this topic are methods for bulk fats and oil. Bulk fats and oil meaning, you know, your canola oil, your olive oil, your lard, your coconut oil. So these are bulk. You buy them as use them as ingredients or raw material for your process. We're gonna cover a little bit of physical characteristics. We're going to talk about iodine value, supplementation value, which we'll be doing in the lab. So we'll be doing iodine value, supplementation value. We're going to be measuring free fatty acids and link it to oxidation. The higher the fatty acid, the more the oxidation, and see how it differs from a refined oil versus non-refined oil. We're going to talk, you're going to do in the lab peroxide value, which is measuring the present state. So you get the oil. What is the present state of the oxidation? Peroxide value is one of the measures for primary lipid oxidation products. And then in the lab, we're also going to address stability. So what CAP is going to do for you, they're going to put the oils at high temperatures for certain different time points just to accelerate oxidation. And then you're going to evaluate the stability of these oils over time and compare different types of oils to each other based on the degree of unsaturation, based on the level of free fatty acid. So the higher the degree of unsaturation, the higher amount of fatty acid, the more oxidation you're going to see over storage. So you're going, it's a very nice lab, one of my favorite labs where you kind of link things together based on the composition of fatty acids. We're going to talk briefly about looking at the different lipid fractions, cholesterol, trans fat, saturated, unsaturated with these methods. All right. So what you want to consider, first of all, sometimes you don't have bulk fats or oil. Sometimes you want to look at the composition of the oil or the fat component of different food products. Or you want to look at the stability of the fat within a food matrix. So what you want to do is you extract the lipids first. So if it's not an oil or a margarine or a butter or whatever it is, and it is, let's say, oats, flour. So you want to extract the oil or the fat from that flour using hexane or other solvents, a combination of other solvents, batch extraction. Get rid of the solvent and then get the oil, and then you can characterize that oil that you have extracted. Some previous capstone students needed to look at oil peroxide value or within their products to look at stability. So they would extract the oil, evaluate the current status of that oil within their product. But we have to be careful on how we handle our samples before analysis. So We don't go and open the oil bottle a week before lab, for example. Exposed to oxygen, exposed to light, potentially changes in heat or temperature in the room. So we want to avoid all of this while we're waiting to analyze our sample. Otherwise, we'll get erroneous results because heat, oxygen, and light is going to speed up oxidation, and then our analysis will be erroneous. Okay, so please, this is a good intro for you. I will be back to continue with this lecture Monday after Thanksgiving. All right. Well, have a great Thanksgiving, you guys. I won't see you until after.